So you have a car, it's traveling along, it sees an accident. When it sees an accident, how fast is it going? 100 kilometers per hour. That's its velocity, right? How far away is the accident? 80 meters. It's 80 meters away. So the question is asking, what constant deceleration do you need at least in order to stop before the accident? So really you're translating this to be, what constant deceleration do you need to stop in exactly 80 meters? That's really the math you're doing here. So if you find that out, if you decelerate any faster, you'll definitely stop before 80 meters. What's the first problem you run into in what I just wrote down right there? What's the first issue? You have kilometers and meters. You have to be very careful. You can't mix and match here. You have to have one or the other. So you make a choice at this point, and hopefully you make the choice at the beginning. It's really annoying to have to rework these problems if you use the wrong units and go for a while, because you might square or do some weird math, and it might not just be as easy as moving a decimal. So what do you want to go to? Do you want to make everything in meters or everything in kilometers? You sure? I'm going to overrule you here. I don't like going to kilometers. I don't like going to kilometers. Why?
The numbers are too big.
I don't like using decimals. Okay, I want to be juvenile here. I just don't want to use decimals. So instead of using 100 kilometers an hour, I'm going to say what? 100,000 meters per hour. I'm just going to say 100,000 meters per hour. I prefer using 100,000 than 0.08. Is that okay? We don't know what the acceleration is, but what's the key facet about the acceleration that we know? It's a constant acceleration. We know it's decelerating, so it's going to be negative, but do we put in a negative sign? No, the negative sign will generate itself. Our answer should be negative. So call it C. So if that's our constant deceleration, what's our velocity going to be? And we use time here, plus d. Why do you plug that d on the end?
Because there's a variable.
Yeah, you don't know how fast it was going when it started. Well, you do because it gave you the 100,000, but when you anti-differentiate, there's a constant that's along for the ride, because when you take the derivative of a constant, what happens?
It goes away.
It's gone. So what's the antiderivative of velocity? Position. Position. So you end up with c over 2 t squared plus dt plus e. Now another naming convention you could use, you could say C1, C2, and C3 if you wanted to. I like using different letters because we're not using that many. You usually use those index counting terms like C1, C2, C3, C4 if you had a ton more variables. We don't have that many. Let's also write down what we know. We know that the velocity at time 0. What's the velocity at time 0? And we'll say that this right here is time 0. What's the velocity at time 0? 100,000 meters per. Oh, it's so big. What's the velocity at time stop? This is where t equals time stop, is 0. It stopped, hence time stop. What is the position at time 0? How far is it gone at time 0? 0. You can do this from a different perspective. You could say at time 0 it's at 80 and it goes down to there. It messes things up a little bit. You can do it that way. This perspective, I think, works the best. And then what is the position at time stop? 80. You now have enough information to generate simultaneous equations which you can use to solve for C. So you know the velocity at time 0 is 100,000. So where can you plug that in? You plug it into the velocity. So you know that v of 0 is 100,000, but that has to equal what? 0 times c plus d. So what does d equal? 100,000. So now once you have d, what's your new velocity function? Sorry, what's your new velocity function? V of t is equal to ct plus what? 100,000. And you also have a new position function. What's that? C over 2 t squared plus 100,000 t plus e. Okay, so we've used the first one. Let's use the second time stop. What do you know? Oh, let's go to here first, I guess. S of 0. Where can we plug that in? We plug it in right here. And what does that tell us? 0 is equal to 0 plus e. So what does e equal? E equals 0. So now you rewrite immediately. So you know S of t is equal to c over 2 t squared plus 100,000 t. We now have S of t and we have v of t. What's in both of those? C and t. We haven't used two pieces of information. We haven't used any of the information at time stop. We haven't used anything at time stop. So what are we going to plug in? Time stop into both of them. What's the velocity at time stop? So if we take this information and we know that the velocity is 0 when time is time stop, we end up with that equation. What's the position at time stop? No. 80 is equal to c over 2 time stop plus 100,000 time stop. We substituted in these two pieces of information right here, and we ended up with those two equations. How many equations do we have in that bottom box? 2. How many variables? 2. So theoretically, can you solve for them?
Yeah.
Yeah. Which one are we trying to get to find our answer that we're targeting? We want C. We want C. You might find TS along the way and then plug it in, but you can go directly to C. And if you do this out, you end up with, again, we're in meters here, so it's actually going to end up with 62,000, I think it ends up like this, if you do this. It's big. It's really, really big. If you kept it in kilometers, what do you end up with? 62,500. So it's a little better, right? And if you go to meters per second, what do you get? Second squared. You get like 1,700 and something meters per second squared. Are any of them particularly nice?
No.
I do agree, though, that the nicest looking one of those three, I think, is kilometers per hour squared. Then again, is that a very standard acceleration? No. Again, the most common stumbling block some people get to hear, and then what do they mess up? Nothing to do with calculus. They mess up the algebra. If you're dealing with accelerations, you're going to get weird numbers. You expect to see things like 80 feet per second or some velocity, right? Accelerations can look really weird. Okay, so this one you can do without logarithmic differentiation, but logarithmic differentiation will make it a little easier for you. You have y is equal to 10x cubed over the square root of x plus 1 all to the fourth. I'm telling you to use logarithmic differentiation. All that really means is take the natural log first and simplify before differentiating. You're trying to find y prime, so take the natural log of both sides. Why do you take the natural log as opposed to just basic log or log base 7 or log base 12? What? Why is it nicer? This is a really kind of, I get another juvenile answer. It's shorter. I literally think natural log is used more frequently than log because it's less letters. I literally think that's true. It doesn't change anything about the math at all, except you get to write ln as opposed to log. So you write ln of y is equal to ln of 10x cubed over the square root of x plus 1 to the fourth. The whole point of this is you now have logarithms in play, so there are certain rules that only apply when logarithms are in play. What can you do with the exponent? And what can you do with division? And what can you, so you end up with 4 ln of 10x cubed minus 4 ln of the square root of x plus 1. What's the power when you have square root? So you have this ln of 10, we'll leave it together here for now, minus 4 ln of x plus 1 to the what power? But what can you do with that 1/2? Bring it to the front. What does the front become? 2. And what happens when you multiply two things inside a logarithm? What does that mean? What do? You add them together, right? So you end up with ln of y is equal to 4 times ln of 10 plus what? X cubed minus 2 times ln of x plus 1. Have I done any calculus yet? Have I done any calculus yet? Not really. All I've done is expand this right here. All I've done is expand this. What can I do now at this point? What can I do now at this point? You can differentiate it, exactly. You're differentiating with respect to y. Sorry, with respect to x, excuse me. So what do you end up with? What's the antiderivative of ln y? Not antiderivative, the derivative. 1 over y times what? dy dx, y prime, is equal to what? What happens to that 4 ln 10? 4 ln 10 is a what? It's a constant. So what is the derivative of it? 0 plus what? 4 times what? 1 over cubed times minus 2 over what? X plus 1. Some stuff collapses. Now, what are we trying to isolate here? Y prime. So y prime is now going to equal y times 12x squared over what? Minus 2 over? We're almost done. What do we need to get rid of?
Y.
Do we know what y equals? Yeah, we know what it equals. So it's, was it 10x cubed over the square root of x plus 1 times, do things cancel here? 12 over x minus 2 over to the what? Oh, is it to the fourth? The whole thing is to the fourth, yeah. There it is. And that's not a bracket, that's a parenthesis right there. So does it clean up kind of nicely? Yeah, overall, it seems like it's a little bit more work because it's more lines. But what you're doing is you're breaking down a harder problem into lots of little pieces that are much harder to get wrong. It's much more consistent if you do it this way. It's also a good tool to have. One way to attack exponents is with logarithms. Okay. Just be careful and calculate the areas of triangles carefully. Give me the answers here. So what do we have here? 0 is going to be 0 and then what? 1/2 and then 0 and then what? Oh, it's going to be 0 again, right? And then what's 5? 3/2 and what's 6? 4. And you know that if this was straight line, you know that this would be a 3/2 right there. So you know this has to be greater than 5.5. That's the only thing you can say for certain. So your estimate could be like 5.6. So here's a question. Where does G have a maximum value? Be very careful. Where does G have a maximum value? At 7, yeah. What would be the most common incorrect answer? 6. 6 is where the greatest value of f of t is. That graph is f of t. It's highest, f of t is highest here. But G, what is G? G is the area under this, the net change under this curve. So where is it greatest? 7. For this section. Right. As long as it stops there. As long as that's the only part of the function we're looking at. G of 0 is 0, you sure?
Yeah.
Positive? Good job. Way to stick up for yourself. G of 1? G of 2? 5. Straight line, man. 1, 2, 3, 4, and 1. It's 5. G of 3. What's G of 3? G of 3? 7. And what about G of 6? What do we think here? So it's 7 all the way to there, right? So that's 3. So where's 6? 6 is right there, correct? So you're subtracting 1, 2, 3, 4 of them. You're subtracting 4 of them. So what do you get? 3. I'm not disagreeing. I'm just doing it out. It's fine. Where is G increasing? From 0 to what? 0 to 3. Yeah. It's from 0 to 3 because afterwards it's losing net change. The net change is becoming negative. Where does G have a maximum value? T equals what? Yeah, you can say x equals 3. You know, it's actually, you're right. It's x equals 3 because you're integrating on x. Sketch a rough graph. So what does this look like? It's 0, and then what does it become? 2, and then what? 5, and then 7, and then what happens? And what's G at? What's G of 6? 6 is what? 3 right here. So what does it look like? Kind of goes, and then like that. And it's going to keep on going down, right?
Yeah, flattens out a little bit.
It flattens out a little bit. So what happens? It's going to lose. How much is it going to lose on it? It's going to lose 1 more, right? So it kind of goes like this. Does that look good? Yeah. Yay, good job, guys. Okay, what's G of negative 3 going to be? 0 and 0. What about G of negative 2? What do you think it's going to be? Negative? Why is it negative? It's not negative. You want the area that's greater than that, right? Base 2 times 3 is 6. Half of 6 is 3. A little bit more than 3. So what is it going to be? 3.2. I like that. Good. What about G of negative 1? Oh, excuse me. No. Negative 2 is right here. Sorry. 1.6. It's more than it.
It's 1.2.
Like 1.1, 1.2.
Oh, I can't do basic math, huh? I can't do basic math. I do. It's amazing. I get so much practice doing algebra, and then it's just changing gears. It just punches me in the face, huh? So it's a little bit greater than what?
1.
Yeah, so 1.1 sounds good. Sure. What about g of negative 1? What's that going to be?
3.2.
3.2? I like that. It has to be, it has to be a little bit greater than 3, but more than 0.1. It's all an estimate. What about g of 0?
4.78.
So that's going to, you add that, it's going to be 1.5. It's going to be, sorry, not 1.5. That's about 3, right? And what's that? 1.5. So 1.6 puts 3.2 is going to be what? Around what?
4.7.
It's like 4.7 or 4.8 or 4.9, right? So how about 4.8? Sure. It's an estimate, right? You guys really don't like estimating, but you get all angry and squinchy nosed or something. On what interval is g increasing? -3 to 0. Nice. Where does g have a maximum value? X equals what? 0, right? Because it's going to decrease after 0, right? Sketch a rough graph of g. So we do this out, and we know it's going to start here. It's going to go 0 there and 0 here, correct? So then at -2, it's like 1.1. And then what is it? At -1, it's 3 point something. And then what is that? It's 4.8. So it's up there. But then afterwards, what's going to happen? So it's, yeah, so whatever it does here, what is it going to do on the other side? It's going to do the exact same thing, right? Something like that? Does that look right? Yeah. Looks pretty good. Okay, so that's the rough sketch right there. Now, here's what it says. This is g, so it wants you to graph g prime. It wants you to graph g prime. So you've done this before. Remember months ago, you had a graph and then you had to sketch the derivative? You have the graph. It's the blue one right here. So you have to sketch the derivative. Where's it going to be 0? Where's the derivative of this 0? At 0, correct. And then it looks like it's going to max out. So what should it almost be like? Or what's it going to look a lot like? F of t, exactly. Yeah, it's going to look a lot like it. It's going to look a lot like it. The fundamental theorem of calculus part 2 tells you this right here. The fundamental theorem of calculus part 2, this is important, is what allows you to evaluate definite integrals. It allows you to evaluate definite integrals. What's easier for you? A little tad easier. What's the general antiderivative of 4x? 2x squared plus 3x. And what do you usually put here?
Constant.
Why don't we write that in? Well, because you're going to subtract it from itself. So what are you going to end up with? C minus c is always going to be 0. So now you just plug in. So 2 times 8 squared plus 3 times 8 plus c. And what are you subtracting? 2 times 2 squared plus 3 times 2 plus c. What cancels? The c's always are out of there. So you end up with a numeric answer. 2 times 64 plus 24 minus 8 minus 6. Does that sound right?